Hello, and welcome to our simulation-based demo on target wake time. I am Claudio Casetti from Politecnico di Torino. Wi-Fi as a technology has been around for quite some time. Its tenets are based on the principles of CSMA-CA. They include carrier sensing to assess the state of the channel and random backoff if the channel is busy or the last transmission resulted in a collision. Although this is an efficient mechanism when it comes to collision resolution, it, however, introduces randomness. It means the timing of channel access and successful data transmissions cannot be predicted deterministically. Several works in the literature have indeed proven that in saturated networks, the variance of access delay increases exponentially with the number of stations. Therefore, one can't reasonably offer delay guarantees in saturated Wi-Fi networks. And as a conclusion, the original Wi-Fi technology is unsuitable for time-sensitive networking. Enter target wake time. This feature was originally introduced in 802.11ah, but then it became a staple of Wi-Fi 6 with the 802.11ax amendment. It was originally devised to reduce power consumption and improve battery life of Wi-Fi stations, especially those of the Internet of Things. The idea is that devices can schedule specific times called TWT windows and wake up from a low-powered doze state to communicate with the network, namely with the access point. During the doze state, new packets are placed in a buffer and stay there until the start of a new TWT window. Now here comes the trick. If TWT is used to enforce doze times on all stations but one, there would be no access contention because that one station would be the only one allowed to use the channel at that time. So, by properly scheduling TWT windows, and with the appropriate knowledge of the traffic pattern of the stations, deterministic channel access and transmission delays can be obtained. In this way, time-sensitive networking can be supported in Wi-Fi. We simulated TWT in the NS3 simulator, a widely used simulator in the research community. We imported an existing project by Shyam Krishnan Venkateswaran from Georgia Tech University. The original project introduced TWT and provided an energy model following the TWT procedure. We have added on top of it the measurement of SNR and RSSI metrics and a report manager to analyze the output and provide a deeper insight into the network performance. In the simulator, an access point schedules individual stations by sending them a TWT accept management frame, which includes the next target wake time for that station. As explained, the operations of the stations are then summarized in a report manager in CSV form, providing metrics for RSSI and SNR, age information, and energy consumption. An example of the operations is shown in this slide. In it, we assume the access point has a knowledge of the size of individual stations buffer, communicated beforehand. The timeline of events following the transmission of a beacon includes the times at which stations receive data from their upper layers, marked as T0. Then T1 instances identify the time when the station's scheduled wake time begins. The scenario we simulated comprises 8 stations that are scheduled by the access point. Each station is placed 2 meters apart, vertically or horizontally, from another station. The simulation parameters are shown here, including the size of the buffer, the transmission power, and the T0 and T1 times when stations are scheduled. The metrics we collected are the latency and the energy consumption. This animation shows the transmission of the beacon and the subsequent scheduling of all 8 stations, each of which sends UDP traffic, which is then acted by the access point. This diagram shows the timeline of all transmissions that occur in the simulation. Finally, we show you some sample results in terms of latency, where we compare the average latency as a function of the payload size experienced by all stations. Blue dots and lines show communication using TWT, while yellow lines refer to the standard Wi-Fi communication with no TWT and regular contention. It can be seen that the latency guaranteed by TWT is basically deterministic, growing linearly with the payload size. Even more striking is the great saving in terms of energy that TWT allows, which is shown on the right plot. These results can be explained looking at the details of energy consumption. On the left, using TWT, we can see that energy is only consumed during the active window, whereas the rest of the time the station dozes and therefore consumes little energy. On the right plot, when no TWT is used, it can be seen that most of the channel time is spent either receiving traffic from other stations or sensing the channel or transmitting, with very little idle time. Thank you for your attention.